Please, thank you. Well, thank you for the very nice invitation. Actually, it's my first time in Paris. I've never been in Paris, so it's a great pleasure to be here and to give this to talk about this paper that came out in August. So this has been a sort of a long program that has initiated some years ago about how to construct symmetries from a sort of holographic or a string theoretic point of view of various quantum field theories. And well, we will see that the results of this paper, they will connect some topics which are very recent, so I would call it generation Z topics, with topics that are classic in physics and more like Humer's topic, like the Myers effect of the brane dynamics or Hanany-Witten moves. So, okay, well, let's proceed. And let me first, you might very well know about this, but let me first motivate why, we don't need to motivate why we study symmetries in a quantum field theory, so they constrain a lot of the data of the quantum field theory. But let me try to motivate why we need to extend this notion of symmetry. So in particular, one question that one could ask is, can IR strongly coupled phase of quantum field theory be characterized in terms of some symmetry realization, meaning that the phase transition of the phase transition are described by some symmetry breaking. So this is somehow the Landau fantasy or the Landau paradigm. And we know that it's not true if we just consider standard symmetries. And that's one of the motivations why we need to generalize the notion of symmetries. And a first result of this generalization is a sort of theoretical definition of confinement and deconfinement in gauge theories. And this is described in terms of Wilson loops, whether they have a perimeter or a halo. And these the vacuum expectation value of the Wilson loop indeed are a sort of order parameter for symmetry. For example, the one-point symmetry that I will introduce in a second. And finally, there is also another principle which is very useful in order to constrain the IR strongly coupled phase in quantum field theory, and this is Hooft anomaly matching. And for example, a Hooft anomaly can be matched in the infrared by gapless mode, for example, a CFT or a free theory, or a gap topological quantum field theory, or even a gap trivial theory. So, well, by now I think you know this very well, but let me go quickly through the first generalization, which is IR for symmetries. In particular, we can have, for a standard zero form, we can have a conserved current. So 1 for current, which is conserved in this way, and we can generalize to a P for a symmetry. So we have a P plus 1 for current, which is conserved as well. And this defines a continuous P for symmetry. With this conserved current, we can define the charge operator by, so the charge operator is the integral on a D-1 manifold. So this is in Euclidean space of the edge of the current, and this can be done also for symmetry, where the integral now is on a D minus P minus 1 dimension. Then we can define, using this charge, we can exponentiate it with a parameter, and we can define a symmetry operator, UG, where G is the EI lambda, and EI lambda is a sort of E1 group element in this case. So this is for the abelian case, but it can be generalized to non-abelian for 0 for symmetries. And it can also be defined, again, on a higher codimensional manifold to so we can exponentiate this charge in order to define, the symmetry operator for a P-form symmetry. And usually, this symmetry operator, they can form a group law, meaning that UG times UG prime equal to UG double prime, where this is the group law that I have in this case. So generically, this is well, not generical, but this is a situation that usually happens in quantum field theory. And finally, but it's important that the symmetry acts on something, or something that is charged under the symmetry and is present in quantum field theory. For example, the standard 0-4 symmetry, they will act on local operator defined on a point. So the d-1 dimensional manifold surrounds this operator. And when you collapse this operator to zero sides and you pass through the operator, this will generate the group element that multiplies the operator. So this is the action of the symmetry topological operator on the charge operator. And in a similar way, this can be generalized for higher codimensional manifold. Now, instead of a point-like operator, we have a extended operator, for example, a line, and then the topological operator, this is a sort of three-dimensional drawing, is a circle that when you collapse and you pass through the line, generates this phase action on the extended operator this time. So this is the higher for symmetry. And in particular, these last two points, they actually apply also for discrete and finite symmetry. So you can actually define the topological operator for discrete and finite symmetry that act on local or extended operator in this one.
Only the abelian case.
For symmetry, only the abelian case, because you can actually move the operator around without passing the topological. If you have two topological operators, you can move them around and they don't have to go through each other. Whereas for 0-4 symmetry, they have to actually go through each other. So one, basically, there can be they can be non-abelian indeed. So what we learned by studying this higher form symmetry is that there is a general law, is that symmetries are equal to topological operators. And in particular, usually symmetries are defined, are defined by this topological operator, which have a composition rule that are group laws. And so think about the Rubik's Cube as a physical system, and we know that the symmetry, in this case, they form a group, and this is actually the Rubik's Cube group that rotates the Rubik's Cube. The first generalization of this, is there a question? The first generalization is that this topological operator can fuse in a group law, but sometimes they can generate higher codimensional topological operator, which means that different the symmetry of different degrees, for example, 1-4 symmetry and 0-4 symmetry, mix in what is called higher group symmetry. So this is the first generalization. There has been a lot of work in this direction in quantum field theory from lower to higher dimension. They show up in many cases, but I won't focus on this for this talk. But what I will focus on will be non-invertible symmetries. So non-invertible symmetries, they have a fusion rule, so a fusing topological operators, which is more general than a group law. And in particular, it comes with a sum over some coefficients. Usually these coefficients are numbered, but sometimes they can be also partition function of topological field theory, as we will see. And this will happen in higher dimension. And what does it mean in terms of the Rubik's Cube? That as a physical object, we consider also the Rubik's Cube on fire. This means that we cannot only have map in this direction, but not in that direction, right? So this will correspond to the inverse of this map that doesn't exist. So this generalization of symmetry is also called, also fits in this categorical language. So you might have heard by now that there are these categorical symmetries, and this is where the field is going towards generalizing symmetries from group to categories. But yeah.
So can you still call this a symmetry in the usual notion that gives something invariant? I mean, okay, you could respond to some concerned object, but so what? Why do you call it a symmetry?
Right. So in particular, I mean, it shares a lot of properties with symmetries. For example, that you can gauge it, you can find anomalies for it. So they still like constrained constrain the physics of your system. So in that sense, you can generalize. You can talk about.
Is there categorical noether theorem?
Categorical noether theorem. So these categorical symmetries are usually discrete. So going to continuous, it's it's a big question mark. But I mean, I agree that one should study also the continuous case in a categorical language. At least the example I know. But anyway, this is where the field is moving towards, the study of symmetries. So, okay, the first very nice old example that we know of non-invertible symmetries are non-invertible symmetry of the 1+1D Ising CFT. So the 2D Ising model has 3 topological lines, the trivial line, so the identity. This generates the identity. I mean, it's just the identity, it doesn't do anything on the operator, just maps the operator to itself. Then there is a Z2 symmetry. So the Z2 symmetry, it's a standard zero-form symmetry, so it's a topological operator which is codimensional 1, and in 2D is a one-dimensional line. And it acts on the spin operator by flipping the sign. And then you have also a duality operator, which is called Cramer's Vanier duality. And so it's a duality, but at the critical point, the CFT, the Cramer's Vanier duality says that the Ising model is equal to its dual, which is the Ising model quotient by Z2. So the fusion rules are indeed not standard. So in this at the critical point, since it's a self-duality, this operator, topological operator, can be thought as a symmetry of the theory, and the fusion rule for this topological operator are in this. So eta like fuses with eta given the identity, so that's invertible. But the Cramer's Vanier duality defect is non-invertible because it's 1 which will lead D times T will give you 1 plus the eta topological operator. So it's, you see that it's the the manifestation of this non-invertibility. But another manifestation of the non-invertibility is indeed the action of this topological operator D. So this is D on the spin operator, and if you sweep across the spin operator on the other side, what you get is the disorder operator attached to the Z2 line. So one of the manifestations of this non-invertibility is that the non-invertible defect act of some operator present in your theory and don't preserve the dimensionality of the operator. In this case, you get a line attached to a point. So this is another feature of these non-invertible symmetries. So what is called non-invertible action on some operator, which is present in your theory. So you might have already encountered this example. This is in 2 dimensions. And the question that has been studied more recently is, can we generalize this type of symmetry to higher dimension, in particular to 4 dimensions?
Sorry, could I ask a question?
Yeah.
Hi, I'm online. Would you mind going back to the previous slide? And I didn't quite understand what kind of operator you were getting after you had moved the defect. Like what is this?
On the right-hand side?
Yeah.
So this is a zero-form symmetry. So you have a Z2 line, which is a sort of Wilson line for the background field of the Z2 symmetry. And it's attached to the disorder operator.
So you get a web of defects.
Yeah.
Intersecting.
Yeah, you get intercepting defects. So this also mu is also a defect operator, and it attached to the background Z2 line, the background for the line for the background Z2 symmetry.
Okay, thanks.
So this was done. This was done in this paper. They do it very explicitly. So I really recommend it, and it's a very nice paper, very explicit. So this paper by Chang, Lin, Shao, Wang, and Yin, where they show this actually how this action is implemented. So I want to focus more on the 4D example, and I will show you how this is implemented from another point of view. But for the 2D model, there is a very nice section about this in this paper. Okay, good. So, right, and these symmetry have been generalized to 4 dimensions, and they proliferate in higher dimensions. So they are not just sporadic; they actually appear in many examples. An example that we are very familiar with, for example, QD, or even theories. Theories that are phenomenologically relevant. And indeed, by applying, so there have been already some sort of application of these non-invertible symmetries. So this is just to motivate a bit what these non-invertible symmetries are useful for. In QED, so QED has a non-invertible chiral symmetry. And this non-invertible symmetry has been used to fix the magnitude of the topological coefficient in the pion Lagrange. And this is given in terms of the periodicity of the pion, which is F pi. Another application to motivate the study of this non-invertible symmetry has been that by breaking non-invertible symmetries by monopoles, this leads to exponentially small neutrino masses. So these are the 2 kinds of application in 4 dimensions that have been presented. It's still pretty, recent. So people are thinking about this application in the phenomenological world.
Actually, do you need this fancy, can you show back? Do you need this fancy language to fix the coefficient of the...
Right, so this is a good question. So this was done already by an ABJ anomaly matching, but usually you don't match ABJ anomaly, you match Hooft anomaly. From the sector, from the pion Lagrangian sector, F, it's basically like a flavor symmetry, so you can really think about, okay, ABJ anomaly in this regime is fine. It's like a Hooft anomaly for the pion sector, but in a more systematic and quantum field theory language, what you really should match is a non-invertible symmetry in this case. So the 2 things are correlated. I won't explain how to derive the non-invertible symmetry from the ABJ anomaly, but the 2 things are very closely related. Okay, so this is the outline of the rest of the talk. So I will show you a setup where you get non-invertible symmetry from gauging some symmetries, some other symmetries. And then I will describe this holographic construction, which is very well known. And I will, using this holographic construction, I will show you how to derive the non-invertible symmetries from supergravity and how to also construct this non-invertible symmetry from the branes in this supergravity background. And finally, if I have time, I will tell you a couple of words about the air phases and domain wall physics from supergravity. Okay, so let me be very general. Let's have for the moment. And then I will specify which theory I'm talking about. But this is more general. It can apply to a class of theories. So let's consider a 4D QFT with which I call it T. And it has the following operators. So the following spectrum of local and line operators. So I have a spectrum of local operators defined on a point. And I also have a spectrum of line operators, M1, defined on a 1-dimensional map. In this theory, I have a 0-4 symmetry, which is specified by, it's a bit specific here, but to connect with the theory that I will tell you in a second, this is a Z2M symmetry. It's a 0-4 symmetry, and so it's defined by codimension 1 topological operators. So codimension 1 in 4 dimensions is a 3-dimensional operator that acts on local operator with a phase, with a 2M root of unity phase in this way. And also it has a fusion rule, which is a group law. So D3L1, D3L2, it gives you D3L1 plus L2. I also have a 1-4 symmetry, which acts now on...
And it's not the property of the defects property of the operator.
Yeah. And it's like, yeah, it's a property of the operator, not of the defect. Yeah. In particular, I mean, usually you take 1 and 1, and what you get is the D2 operator. Yeah, but
It's the same operator.
yeah, it's
It's a different angle.
yeah. It's different. So then you have a 1 for symmetry, which is a ZM1, and this is defined instead of a codimension 2 operator, which are surfaces, so D2, and they act on the line with the ZM root of unity in this way, and they also have a group law fusion rule similar to the zero force. So I have two group-like symmetry. One is a 0 for symmetry, one is a 1 for symmetry. And in this theory, I assume, well, there is a mixed anomaly between the two symmetries. So in particular, there is a mixed anomaly, which is has a coefficient 1 over 2m, or 2 pi I over 2m. And it's a mixed anomaly that depends on the background field for the 0 for symmetry, A, and on the B2 cap B2, which is the background symmetry for the 1 for symmetry. So, this is an element in H1 of Z2M. It's a 0 for symmetry background, and this is an element of H2ZM, which is a 1 for symmetry background. So the background, for continuous symmetry, they usually couple to the current, so they have the same, indices as the current. So in case of a 0 for symmetry, you have a 1 for symmetry a 1 for background, or an element of this chronology, and a 2 form for the 1 for symmetry background. Yeah.
Can you explain for the non-expert what is this symbol?
So this is a cup product. So we will see that when we go to supergravity, this will be just wedge products. Yeah.
A bit confused by the notation.
Yeah.
The group law is D3 to the M to D1, right? It's two M's, actually. So what is the meaning of this group law of fusion? You apply the operator you apply D3 on some local operator of charge L1. Yeah, I think I'm confused here.
So
you have two spheres with acting on the same.
Yeah. I mean, the operator inside the charge of this operator is specified by the charge operator, I agree. So you can you get. So this is a bit an overkill of annotation. I mean, if you fuse to the free operator, what you get it's an operator which is labeled by another group element. So
the charge is 1, charge of O is 1. And
yeah, or you can think like charge of O is 1, and this is a power of the operator.
So L was indeed the charge.
like copies of the T1.
Yeah.
Okay. Now
you can think about that. Yeah. Sorry. Okay, so we have this anomaly, and what happens if we place this D-free defect on the theory? So we place this free defect on the theory, but the anomaly basically pulls back onto the defect. So which means that if we now do this shift, B2 going to B2 plus D lambda 1, which is the 1 for symmetry transformation on the background B2, this D3 picks up a phase where M4 is a sort of space which has D3 as a boundary, where M3 as a boundary and D3 is defined on M3. So basically, this anomaly pulls back onto this defect. And what happens if we gauge the 1 for symmetry? So suppose we gauge the 1 for symmetry. So now what gauging, it means that we sum over this configuration, like non-trivial configuration of B2 in ZM. But I will denote it by just small letter here. We're going to small letter. It means that this operator is not gauge invariant anymore. So it has a gauge ambiguity. And so we need to fix this operator because we want gauge invariant operator that define our topological operator that will give us the symmetry. And there is a new definition of this gauge invariant operator, and this new definition of the gauge invariant operator dresses the D3 with a topological field theory, an abelian topological quantum field theory that cancel this gauge ambiguity. So you dress this or the D3 with this theory, and this theory will generate the anomaly with the minus. So now we fix this operator by adding this topological quantum field theory. And for example, for AM, 1, this is indeed a 3D Chern-Simons theory in this case. with the Chern-Simons level M, and it's a U1 Chern-Simons theory with the Chern-Simons level M. But the price that we have to pay to once we define this new operator is that if we try to compute N3 and N3 with its complex conjugate, or if we try to find an inverse of this operator, there is no inverse, meaning that this is not equal to the identity, but it's rather a complicated topological operator, which is called condensation defect, and it's a mesh of this holonomy on a three-dimensional space. So this will be a two-dimensional holonomies, M2, where M2 are embedded into M3, and so it will depend on the topological detail of this space, but it's a mesh of these two-dimensional operator which form this condensation defect. So this is a complicated, so there have been studies on these operators, so there is a whole line of research on these operators, but just the important thing is that this is not the I mean, you might think that this symmetry is unitary.
Should take N3 minus 1.
Yeah. But, well, this is, the non-invertibility is not just encoded here. So this is a one instance of non-invertibility, but you might think that the complex conjugate is the inverse, but it's not, because it doesn't give the identity. But also you might try to look at other fusion to find the inverse, but you see that this is actually gets more complicated. And
the right-hand side is a projector or not necessarily?
And not necessarily a projector. It's basically a sum of, it's a sum of a codimension one operator in this three-dimensional object. It's a mesh more than a sum. So they form junction and so on and so forth.
So if I take twice n and dagger, I don't get the same thing. I get a different mesh.
That's actually, I'm not sure whether you get.
Say twice n and dagger.
Yeah.
No, I think you get the same, because this is a sum. There is a sum over all this possibility. So I think
it is a project.
Yeah. Okay. Yeah, I think so. Yeah, I think you get, if you read twice, it's I'm not sure, but I don't want to say anything. But it's,
I know our project.
Yeah. Yeah.
It depends on A, but A is just a function of the number.
A, no, it's the partition function of the topological quantum field theory.
It depends on B2.
It's coupled to B2, yeah, it's coupled to B2. It's coupled to B2, and it not because it needs to cancel the gauge ambiguity coming from here.
So it's like a value.
Yeah.
So how should I think of normally what kind of object?
So you just, I mean, it's a pretty explicit computation. So you have D3, and then here you take the partition function coupled to B. So for example, you have is for U1 Chern-Simons, what you have ADA plus AB2, and the operator N is given by D3. E, you have also the sum over DA, and then the exponential of this integrated on the space on M3. So this is the explicit construction of the operator, and then you compute fusion with this construction of the operator. And the fact, this is the non-trivial fact is indeed that it's coupled to B2. So it's not just Chern-Simons. So it talks to you know, the D3 that is not gauge invariant.
It's like the stack annotation, but you need a sensible for tensor product and for fusion product.
Yeah, I agree. Sorry. Yeah. I think that's also been misleading in the literature. So, yeah, that's a good point. So the procedure is pretty general. It applies to any theories with these symmetries and these anomalies. But, I mean, you might have figured out by now that the example I'm talking about is n equals 1 super n means. N equals 1 super n means has exactly these two symmetries. is exactly a Z to M04 symmetry, which comes from a, the R symmetry that is broken quantum mechanically by an ABG anomaly. So the U1 is not realized quantum mechanically, but what is realized are this value of the phase of U1, which means that this is a Z to M symmetry. And also you have a 1-4 symmetry, which acts on fundamental Wilson line with a Z root of unity. This theory has also this mixed anomaly, and this has been studied by from quantum field theory and from also other approaches in this paper, in these papers. So it has this feature. And so SUM has the symmetries, has these symmetries with the mixed anomaly. And when we gauge P2, we go to PSUM. And indeed, so actually this should be M, not M. And also that one, so SUM. And indeed, what PSUM has is a non-invertible 0 symmetry. Okay, so we are lucky because there are many constructions. Actually, I will talk about one specific construction that are from string theory. There are string theoretic holographic construction, and these are related somehow to n=1 super n means. And the result that I will present you are that using this construction, we'll be able to derive a bulk topological theory, which corresponds to this discrete and finite symmetry sector. So the symmetry sector that recast the 0 form and the 1-4 symmetry. And also we will see that we can derive this symmetry from, and the topological operators for this symmetry from the brane, this 10-dimensional geometric construct. And the fusion will correspond to of symmetry if that are connected to the Myers effect. And in the non-invertible action on operators of the theory are connected with the Hanany-Witten effect. So this is just a bunch of buzzwords that to present the results, to spoil the result, and then I will describe what this holographic construction means. So let me motivate again why holography in this case. So you have a quantum field theory. This is well known, so you can construct all the symmetry. So why would you study holography? Well, these are some of my personal takes, some of personal motivation that I like. So not all quantum field theory have a UV Lagrangian. So in the case that we described, it has a UV Lagrangian, so you can study the symmetries from there, and then you can match if you have an holographic construction. But not all of the quantum field theory have a UV Lagrangian. So you might need another approach to study the symmetries of this quantum field theory. Moreover, fusion rules from quantum field theory, as we've seen, can be hard to compute. So maybe in holography they simplify, maybe not. Well, this is still an open question, but in some sense, I will try to convey that they kind of simplify.
Holography usually means a large N.
Yeah, it's not actually,
It's more like geometric.
It's more like geometric engineering. But in this case, we use the actually holographic background for N+1, but it's more like geometric engineering. So these categorical symmetries, they seem to be naturally encoded in a framework that actually needs the bulk. So this was this recent mathematical paper that came out, and it seems that in order to encode systematically discrete finite categorical symmetry, you actually need the bulk. So you need this object that is a one-dimensional higher topological quantum field theory in order to describe all the symmetry of the quantum field theory at the boundary. And finally, some other aspect is, can we learn some aspects of gravity from the bulk? So this is not very precise, but who knows, maybe. So the goal is to construct, understand how non-invertible symmetry are realized holographically, or in geometric engineering, from explicit example. And in particular, what we want to do, we want to take 10-dimensional or 11-dimensional supergravity and construct a D+1 dimensional topological action. With this topological action can be called symmetry topological field theory. So the symmetry topological field theory is a topological field theory that encodes the topological operators of the theory living at the boundary, or a D-dimensional QFT living at the boundary, together with the symmetries, because the topological operator are the symmetries. And In particular, this also needs the choice of a topological boundary. Moreover, some general facts are that gauge symmetry in the bulk correspond to flavor symmetry in the boundary, and this topological action can contain also the top anomaly of your quantum field theory in the boundary. So the generic situation that we face in this symmetry TFT, so we have a D+1 dimensional theory, where the radial direction is this +1 direction. So there is a rho, which is a gap boundary. It's a topological boundary condition. And on the right-hand side, there is not a quantum field theory that lives on the right-hand side, but it's rather a relative theory. So what is a relative theory? A relative theory is a theory which doesn't have a partition function. It has rather a partition vector. So naively, you can think as a set of theories, meaning that if you have a gauge theories, you have gauge theory in the boundary, you haven't specified any global form. Gauge theory. So you have all possible global form, and the choice of this rho will specify, once you collide with the boundary, will specify what global form you have. So this is the generic situation that you face in this kind of compactification.
Sorry, what does it mean, global form?
For SU versus PSU, for gauge theories, for example. And in order to specify an absolute theory, which is a single quantum field theory at the boundary, you need to do this collision. So this is not usually what you get in holography. In holography, you don't have this spacing, so you really choose the boundary condition at infinity. But in order to be, in geometric engineering, you can try to deform the background in order to have such a situation, but also in order to depict better the choice of boundary condition, I decide to separate these in the bulk. So the most famous example is the symmetry TFT for n equals 4 super means, which comes from ADS5 process 5 from supergravity. And it's only the topological term containing the B2 force field and the C2 force field, so the SNS B2 and the Ramon C2. So this was studied by Witten, but also more recently in some other papers. And it's basically a BF coupling of B2 and DC2. So this is a symmetry TFT for n equals 4 super means. So this symmetry TFT has this equation of motion. So this, so you get that the degrees of freedom that survive from this equation of motion are B2 and C2, which are holonomies in Zn because you have these two equations. This is what you get from this BF theory. And now we have to pick topological boundary condition in order to specify a single quantum field theory at the boundary. Meaning, in this case, we really specify the global structure and the one-for symmetry of the theory at the boundary. And let me show you two particular cases, which are the two extremal cases. So in one case, we choose B2 to be fixed at the boundary, and we choose C2 to be freely varying. So this is a topological boundary condition, and it specifies the SUN global form for the quantum field theory once we collide the boundary condition with the relative theory. And we can also pick the other one where B2 is freely varying and C2 is fixed. And in that case, we have PSU. So there are also intermediate boundary conditions, but I won't discuss about them. I will focus on these two extremal boundary conditions, also in what follows. So these are also I also draw the brane, but because these holonomies and also the charged operator, like Wilson line or Hooft line, can be also represented as brane stretching along the radial direction, whereas the topological operator are brane parallel to the bound, the link with these other brane infra-red dimension.
So these B2 and C2 come from the reduction of the two forms in ten-dimensional.
Yeah, this is just in 2B you have a topological coupling which is F5 H3 DC2, right? So F5 gives M, and then you get this that time. Yeah, so these are the C2 and B2 of 10 dimensionals. Supergravity which reduced to 5 dimensional.
They transform as a doublet on the rest.
Yeah. Indeed, there have been extension of the symmetry TFT also considered there. So
these things are not necessarily in the ADS spectrum.
are they? In often yeah, but often the higher form becomes massive. It's beyond consistent truncation.
Yeah. But how they, what they correspond about. But if you want to study the symmetry sector, I think you have to keep this topological term. That's what I mean. I mean, I'm studying only the symmetry sector rather than the dynamical sector of the theory. So, okay, but what about n+1 super-Yamis, which is the example I will talk about? So, holographically, there is a construction of n+1 super-Yamis, which is given by related to n+1 super-Yamis, and this is the Klebanov-Strasser background, which is MD-free brane probing the conifold. So probing probing the conifold, which is a cone over this T11 that topologically can be thought as S2 times S3. And then you have MD5 branes on S2. So we will focus on a case where n is equal to kn, at least the constant coefficient. So n actually runs. It depends on the radial direction, but there is a constant piece which is proportional, which used to be proportional to a multiple of n. And then this theory, this background is dual to the chain of cyber dualities and energy flows in this. So it's dual to this cascade, meaning that these theories, which is actually the one dual to this construction, is related to SUM in the AR via RG flows. So these are RG flows, and you see the relations. This theory, they flow basically to the same IR. Good. And in particular, they share a lot of symmetries in common. So this theory will also have a one-form symmetry, which is Zn, and a zero-form symmetry, which is Z2n. So this is important. And then, so you can also study this background in the near horizon limit, where the D5 brane becomes F3 flux on S3, and you see that F5 depends on R, so it runs. So n is not actually completely quantized. So we study this dimensional reduction on S2 times S3, and we study basically the small fluctuation of the 2B supergravity fields around this Klebanov-Strasser solution. So this was done in particular in these two papers, the study of the reduction of T2B on the conifold. And so we look at this action, and what we want to is to focus on the sector that is recast the symmetries of SUM super-Yamis. And the 5D topological action that recasts the symmetries, it's this expression. So we have a C3 field, which is the reduction on C6 on S3. We have A1, which is the Rib vector. So it's the field which is dual to the U1 isometry. And then we have a G2B. G2B comes from the reduction of F5. And this G2B is dual to the 1-4 symmetry. Okay, this is more complicated than the n=4 case, so it's a bit more, the action is a bit more involved, and it's presented in terms of continuous fields. So the BF term, and the Stuckelberg couplings, they set this equation, and the Bianchi identity, they set this equation to 0. So in some sense, they discretize this field. So A1 now is discretized, is the background field dual to the Z2M 0-4 symmetry. And G2 is also discretized by Bianchi identity and is the field which is dual to the ZM 1-4 symmetry. for now, no global form has been picked. In order to pick a global form, we need to study boundary condition, and that's what we're gonna do. We will study the gauge invariant operators and the sort of the topological operator that becomes topological at the boundary, in order to and the possible boundary condition in order to specify a global form. So we do the same as we did in n equals 4 premise, but with this rather more complicated action. Okay, so the strategy is the one that was implemented by Bell and Moore. In particular, so also maybe in other examples, but what we consider is that we consider the radial direction as a sort of Euclidean time, and then we split the field into a radial direction, which is the 0 direction, and times the rest. So we did this splitting, and we rewrite the Lagrangian. In rewriting the Lagrangian, you have a term which is just proportional to the field that depends on this A1 field, which do not depend on the radial coordinate. And you get an L0 piece, which depends on this A0. A0 is the component on this radial direction. So this term is just a Lagrange multiplier action. So by varying with respect to Lagrange multiplier, what we get is the Gauss law. So we get the Gauss law constraints in this. And the Gauss law constraints, they generate the small gauge transformation on M4. So you can integrate this action on an M4 slice of this 5-dimensional space, and then this will generate the gauge transformation. This is a more complicated example, but this also can be done in Maxwell theory. And in Maxwell theory, you can get the Gauss law nabla equal to 0 by doing the same thing, by splitting the 4-dimensional space in a sort of radial direction. And what you get is the time in Euclidean time. What you get is that nabla is equal to 0. Okay, so let's pick this action and let's focus on a particular Gauss law. So one Gauss law that we get is that this GA1, which is given by this expression, is equal to 0. So then we want to define a D-free operator. Since this GA1 is flat, we want to define the D-free operator at the boundary. And for the moment, we will assume, well, I will always assume that C-free. So since this comes in a BF coupling, so you have a choice of boundary condition for C-free and A1. But we will assume that C-free is always freely varied and A1 fixed. Why we do this? Because we want a 0-form symmetry. So we don't want a crazy 2-form symmetry in this theory. So we actually do this. Actually, it's a recent paper that came out of yesterday that actually shows that this cannot be done due to a Hooft anomaly. But sorry, the reverse cannot be done. So you can only do this. But anyway, we assume that we do this in this case. And we study the possible boundary condition that now will depend on G2, because C-free is fixed to be freely varied. So C-free, the holonomy of C-free will define a topological operator. And in the first case, we want G2 to be fixed at the boundary. If G2 is fixed at the boundary, this is just a C number. So the topological operator is invertible and is D-free. And it corresponds to the SU and PSU. Whereas if G2 is freely varying, this is not well-defined. So G2 over 2M is not well-defined. Because, so this is basically like a sort of a derivative of a 3D Simons theory, but with a coefficient that is not correctly quantized. So in order to correctly quantize a Chern-Simons theory, you want the M to be at the numerator, 2M to be at the numerator rather than the denominator. Otherwise, the action is not gauging power. So, and in order to fix this, you actually introduce a new field, A, and you do the path integral over this field A, and this, when you integrate out A, you actually, it reduces to this, but at least this action now is correctly presented and it's consistent. So, and this full topological operator is actually the operator that realizes an non-invertible symmetry. So we construct this operator from supergravity consideration only for PSU. So let me recap a bit of the situation. So we have two choice of boundary condition. Well, two kind of boundary condition. One which specify what 0 form you have, and one that specify one that specifies whether you have a 0-form or a 2-form symmetry, and one that specifies whether you have an electric or magnetic 1-form symmetry, rather whether you have SUM or PSU. But in order, since this Gauss law mixes with G2, we need to collide these two first, and then we need to go at the boundary to really pick up a single quantum field theory. So this is, you remember the drawing for n equals 4 via mist that I had before. This is a bit more complicated because we have more fields in the supergravity action. Okay, so this was the supergravity story. Is there a way to actually encoding these generators in a more intuitive manner? So let's start from the supergravity Gauss law, which I presented before. And let's try to understand what is the 10D origin of this field. So C3 is the dual field of C0, meaning that C0 was the dC0 is the F1 field strength, and F1 is the reduction on F3 on S2. So this is in the conical background, in the Klebanov-Strasser background. But C3 comes from the reduction of C6 on the volume of S3. And what is C6 is the Ramon-Ramon field that electrically sources a D5, and in particular D5 brane on S3. Okay, the proposal is that can we realize this 0-form defect as a pi brane extending on a 3-dimensional slice of the 4-dimensional space, which is in 5 dimensions is again a slice of this, or a radial slice of this 5-dimensional space. And in particular, this brane, since it's a brane that's in the region where, in the large radius region of the Klebanov-Strasser background, is a non-BPS brane. Okay, so let's try to run with this proposal. Let's try to construct what is the effective theory on the brane. So the effective theory on the brane at low energy is the dBi action plus the West-Umino action. So the dBi, it depends on the radial coordinate because you have the determinant of the metric in front of the dBi. And there is an effective tension that comes from this, which depends on where you place these lines. So it depends on the radial coordinate at the third power. Well, where we want to place the brane is the brane we want to put it at infinity, and at infinity indeed. So the first at R equal to R0, where this 5-dimensional background is as a boundary, but then we also want to send this R0 to infinity, and in this limit, the dBi, so the non-topological part of this action, decouples. Basically, it's frozen because it goes to infinity. So the contribution of the partition function from the dBi, it goes to 0, whereas the West-Umino part remains finite. So we are left with the West-Umino part. The West-Umino part has this complicated expression. So you have the Ramon-Ramon field, the sum of all Ramon-Ramon fields, and then you have an A1, which is a field that lives on the brane. It's a mode. It's a U1 gauge field that lives on the brane. It's not a supergravity bulk mode, but it's a mode localized on the brane. And what we do is the reduction of, we integrate on S3 this action, and what we get at the end is this expression. So we get C3, and we get a Chern-Simons action plus a Chern-Simons action coupled to B1. B1, it's a bulk field that comes from the reduction of C4 on S3. So A1 is always dynamical, and B1 is a bulk field. So we have to choose the possible boundary condition for B1. And again, we face two. I mean, we can face many possibilities, but we choose to focus on two possibilities. The first one is when B1 freely varies. When B1 freely varies at the boundary, then we obtain a theory, which is it has two dynamical gauge fields, U1 gauge field, and you can recast this action in this way. And if you recast this action in this way, this is a trivial topological theory, meaning that it's the Z1, if you're familiar with this, it's a Z1 Digraph-Witten theory. Because you can change coordinates of these metrics and basically get a 1 coefficient. When B1 is fixed instead, this becomes a sort of C number at the boundary. And the Chern-Simons now is non-trivial. It's a Chern-Simons theory with level M. And this will dress the topological operator to make it non-invertible. So we also have constructed this non-invertible topological operator from these D5 branes. Okay, so let me quickly go through a couple of properties of these non-invertible symmetries. I guess I have 5 minutes, right? A little more. Yeah.
You mentioned Myers. Where is Myers?
It's coming. So, properties of non-invertible symmetries. And indeed, it's coming pretty soon. So the question is, can we derive fusion rules for this brane? Can we derive the field theory fusion rules from these branes? So there is a fusion rules with fuse N3 with N3 itself. So you want to construct now N3 but since this is non-invertible, there is a coefficient AM2, and this AM2 is not a number, but it's rather the partition function of a Chern-Simons theory. Well, topological theory, not a Chern-Simons. Forget about it. This is the partition function of a topological. And D2, again, is defined by D32, so the invertible part, times this topological theory now, which is coupled to B2. So this part is not coupled to B2, but this part, so it's the same theory, but coupled to B2. Okay, so this is a fusion rule that has been derived from field theory only for M1.
But does it mean not coupled to B2, means some of the whole bus?
Yeah. It actually gives a number in that case once you integrate it. Yeah, once you completely compute the partition function. But yeah, but it can be recollect in terms of a partition function of topological. Whereas the part in N2 is coupled to B2 because you need to cancel the anomaly generated by D3. Yeah.
Sorry, just to be sure, the AM2 without B2 dependence, is it the value at B2 equals 0, or is it the integral over B2?
No, it's the value at B equals 0. It's not integral. Sorry, yeah, I didn't. Sorry. Yeah, it's actually not coupled to B2. It's just, for example, if this was 1, you will get just a Chern-Simons theory without coupling to B2, without the term A, like B2 equal to 0. Okay, so the puzzle is, can we arise this fusion by considering a stack of two D5 branes on S3 rather than one D5 brane. So the stack of two D5 branes on S3 will give a U2 Chern-Simons theory at level M. Right? This is standard brane theory. What you get is a non-abelian Chern-Simons theory. But this is not consistent at all, because on the right-hand side, so these two theories are all abelian topological quantum field theories. But according to from this brane point of view, according to the fusion from this brane point of view, it will tell us that an abelian theory on the left fused to a non-abelian theory on the right. But the spectrum of anions for line operator doesn't match in this case. So this raises a puzzle. How do we solve this issue? Well, this is due to the fact that we haven't considered the dynamics of the brane. So in particular, we want to consider a stack of two D5 branes, and we want to put these at the boundary. But before going to the boundary, we go to R equal to R0, and then we send R0 to infinity. And at R equal to R0, there is a non-trivial dynamics of a stack of K D5 brane, which has this action. So the Xi are matrices in new K here. If I have K D5 branes, they generalize from two D5 branes, I take in K D5 branes. So these are UK matrices, and they parameterize the orthogonal direction of the brane. So they describe the fluctuation of the brane in this space, R times S2. But close to R0, the space becomes flat, so we don't have complication about the metric that is curved. So close to R equals 0, where is the I mean, there is the regime that we look at. This space becomes flat, and there is also a B2 field, which is non-trivial and gives this. This is important. The fact that you have a B2 field that gives this kind. We can study the equation of motion of this action. This is the equation of motion, and the minimal static configuration is given by SU2 reducible representation, which are a matrix of k times k size. What is the interpretation that Magas gave something in the late 90s is that there is a dielectric effect caused by the fact that by the presence of a B2 background on S2, and it means that the phi brane puff up into this S2, meaning that there is an equivalent configuration of a single D7 brane, which wraps the full T11, which also wraps the S3, but it also wraps the S2, and on the S2 you have a flux, a k unit of flux, k unit of flux, where k is actually the same as k, the number of the phi brane. So this is a k unit of the phi brane flux. So for k equals 2, then you can explicitly compute the action of a single phi brane with k equals 2 flux. And the Bohr volume theory that you get is this expression. So you get 2C3 and ADA, so basically twice the value of the single d phi brane. And you also get this value, 2A dB1. And you can show that, actually what we did, we show that via field redefinition, this action is equivalent to the left-hand side for any m. And we also check for m equals 2 and n equals 3 that it gives the right fusion rules from field theory. So this is not, then it's not for any generic n, but at least for generic n, we show that this action is equivalent by field redefinition to this left-hand side. And in particular, this presentation of the fusion, it's just to mention, I won't give you any detail, but there was a paper that came out more or less at the same time, defining from field theory a sort of way of fusing these operators, which rather than giving this expression on the right-hand side, they always give something similar, more similar to this, rather than this factorization on the right-hand side. So what I want to tell you is that it actually it's this fusion that we get from string theory and from holography. It's more similar to the result of the paper by Putrov. Okay, so the last bit is the action on Hooft lines. So you remember that for the Ising model there was this action of the non-invertible defect on the sigma operator. And there is a similar action of the non-invertible defect in 4-dimensional n equals 1 Superbanian means on Hooft line, meaning that once you, so you can see this from this gauging the one for symmetry. So you can gauge the one for symmetry, and then you can place the non-invertible defect and add a counter term only on the right-hand side. If you do this, then upon this, if you do that transformation, then the H line picks up a on the right-hand side picks up a phase ambiguity, which needs to be cancelled by addressing of this flux B2 flux operator. So this is shown in field theory. So meaning that once you sweep the H line across the non-invertible defect, this will be connected to the non-invertible defect by a tube, a flux, a B2 flux operator in connecting H with L. So this is similar to the Ising model, but for this higher dimension theory. So let us recap what are the branes. So the H Hooft line can be constructed by D3 branes extending on the radial direction and wrapping the S2. And the N3 N3 defect, topological defect, is the D5 wrapped on S3 and extending on this direction, so parallel to the boundary. So this is by chain of T and S duality, is related to the NS5 and D5 branes of an Hanany-Witten system. But in Hanany-Witten, we need to be sure about charge conservation, meaning that the total linking number between the two branes is conserved when we exchange the position of the NS5 and D5. But it turns out that the linking number is not equal if we just exchange these two branes. And what we need to insert is indeed an F1 on this direction, on the direction where these two brane links. And basically, this is the Hanany-Witten transition between D3 and D5 in this system, which is dual again to related by T and S duality to the standard original Hanany-Witten setup. And if you sweep across the D3 brane to the D5 brane, this will generate an F1. And in field theory, what this corresponds to is indeed to this non-invertible action on the top. And as another evidence, at infinity, you can see that the F1, the dBi of F1 decouples, and what is left is the West-Domino part, which does the anomaly on B2 on this space. Okay, I think I'm out of time, so let me just mention that we can characterize also the IR phases of these two theories via supergravity, and this basically encodes the dynamics of the domain world, so the domain world physics in the infrared. So whenever the domain worlds they contain a non-trivial Chern-Simons theory for SUM, or they actually contain a trivial Dirac-Witten theory for PSUM. And let me conclude by saying that, so we constructed the bulk action that correspond to the symmetry TFT. So this is a monopole object that recasts the symmetries for n equals 1 SUM super mills. We constructed non-invertible symmetry defects via Gauss law from supergravity, from a particular sector of the supergravity reduction. And we constructed these non-invertible symmetry defects from the brane in this particular. So thanks to the existence of this particular background, we were able to study breaks in this background and propose this brane as non-invertible symmetries, which passed through some checks, actually many checks. So the fusion rule of this brane makes sense only when the Myers effect is taken into account, as we've seen. And finally, there is an action of a non-invertible action of this non-invertible defect on the lines on top line in PSU and super mills. And this is encoded in string theory or in this holographic construction or string theory engineering construction by an Hanany-Witten transition. And some outlook is that so one might think that the condensation of N3 with N3 dagger can be related to tachyon condensation. So you take a D5 and an anti-D5 and can fuse them, but this will give you tachyon condensation. So is there a connection with tachyon condensation with these fusion rules? And it seems that the topological remnant, there is a topological remnant of the tachyon condensation that is actually giving this condensation defect. But this is something that it's not well understood at the moment, but people are trying to understand. So maybe one can look at many holographic and string theory engineering. There have been a proliferation of these inspired by these results. There have been a proliferation of application of these methods in order to study other holographic setting or string theory engineering setting. From n equals 4 super mills and there are non-invertible symmetries even there, which correspond to the dualities, self-dualities of n equals 4 super mills, particular couplings, and this can be engineered, for example, via D7 branes, wrapped on S5. Anyway, there have been studies. And one aspect that is very crucial, I think there are these discrete but non-finite symmetries, non-invertible symmetry, which are called Q mod Z. And is there a way of encoding these symmetries in bulk formalism? So by extending the symmetry TFT to these non-finite symmetries. So that's an open question. I think it's a very nice direction that can be studied. And finally, can we apply this non-invertible symmetry to constrained algebraic plots? There are people are looking into that, and or to constrain circles. For example, this is very well known in 2D, so you can use the Ising category or the non-invertible symmetry in Ising or in rational CFT to constrain the spectrum of operators, to constrain quantities, observables. But what about higher dimension? And this is an unexplored region. And finally, well, a collection of buzzwords that people are trying to make sense of together, whether we can actually, there is a categories of branes that describes these categorical symmetries. So thank you for your attention. Questions?
So when you take the supergravity branes and you fix some kind of Dirichlet condition on the boundary, you have the topological part, but you also have a real defect in the CFT. When you have something that distorts the CFT non-topological. Could be quark, heavy quark, or something else. So I was confused. Can you separate the two? Can you take away the topological part of this?
Yeah. So
and it still makes sense.
Yeah, actually.
So what's the thing left without the topological part?
So you're asking whether, I mean, so the brane.
You know, there is a real defect, and then there is a topological one. When you neglect the DBI action and so on, you only keep basically the topological information.
Right.
My question is whether on the boundary I can separate in any sense.
Right. So you mean going a little bit into the bulk and see what happens, or?
Well, this topological fusion algebra is presumably part of a much bigger fusion algebra where you have real quarks or real strings in the field theory that are brought close together. And this fusion is singular and it's not topological and so on. My question is whether you can factorize the topological algebra. It's probably related to your question about tachyon condensation in some way, but what is known about this?
Well, I think it's still under investigation, that part. What you really realize is that if you focus on the brane, just on the brane, then at the boundary you can decouple, the DBI, and just you're left with the Western action. So it's a proxy for the topological operator. That's what we realize. There is a bunch of other stuff in it that you might want to understand.
But I mean, why is it topological? If I deform the boundary surface,
but as long as it's at r equal to infinity,
then you cannot bring it. Topological means you deform it and bring it to the other operator section.
What I mean is that you can deform the boundary, but you're not deforming the bulk into the bulk. That's what I want to do. So I want to place the brane at the boundary. Deforming the boundary, it's okay. That still preserve the topological properties, but not deforming into the bulk. If you deform into the bulk, then it's another story. Then the DBI starts to matter, and
maybe we can discuss.
Yeah.
Questions? You mentioned this infinite non-invertible symmetries. What kind of system is it?
QD.
Just QD.
No, well, not just QD, but QD is one good example. But axiom Maxwell. These very simple theories. So Maxwell coupled to an axiom has a lot of has a couple of symmetries.
Is Q over
Q over Z.
What does it mean in practice?
As a sort of collection of ZM, nested ZM. This is in the paper by Putrov. It defines mathematically more rigorous way what this Q mod Z means.
So there are some interacting theories which are very relevant. Yeah, okay, QD is in fact.
Yeah, QD. It's the another example. I don't have any. I mean, there are 3D examples with these symmetries, but similar in spirit. So it's not very.
And just add it in the Myers effect you discussed. If you want to phrase it in terms of the sandwich with the SymTFT, can you say that the SymTFT depends on the vacuum that you pick for the quality? So here you kind of move on the Coulomb branch, and then you say the SymTFT changes. So this is what.
Yeah, I think so. Yeah. It's
so SymTFT actually doesn't depend only on the theory, but on the theory plus which vacuum.
Yeah, but right. But in this case, you're rather specifying what kind of defect you want to. It's not just specifying only the.
So you're moving on the Coulomb branches.
Yeah, you're moving on the Coulomb branch of the brane object. So if you want to specify the boundary, which kind of defect you're studying at the boundary, as well as the possible boundary condition, then yes, I think it's what you said. You have to specify also this.
Okay, we can continue with this discussion over coffee. Let's thank again Fabio for the The good thing about the injection is that we do have coffee to offer. If you want to go up, I will bring your glasses. And we talk again at 45.